Last week, we investigated the Orion mystery. This week, we look at a very special number in mathematics, phi, also known as the golden ratio or the divine proportion. Let's start by considering what a ratio is. In mathematics, a ratio compares values. In other words, a ratio says how much of one thing there is compared to another. For example, if we have 3 blue balloons and 1 red balloon, we say that the ratio of blue balloons to red is 3:1. Over 2000 years ago, the Greek mathematician Euclid, also known as the father of geometry, defined what he called the extreme and mean ratio. Over the years, this ratio has come to be known as the golden ratio and as the divine proportion. Why all this fuss over a simple ratio? What is so golden or divine about it? Now, I'm sure most of you watching may not like mathematics, so I'm not going to actually define the golden ratio. Instead, let me simply say that the value of the golden ratio to 3 decimal places works out to be 1.618. It is known as the number phi in honor of the Greek sculptor Phidias, who over 100 years prior to Euclid's birth is supposed to have sculpted the Parthenon statues using this ratio. But this was not the first time that this ratio had been used in history. Long before Phidias sculpted the Parthenon statues, and I mean long before, phi made an appearance in the construction of the Great Pyramid of Giza that we looked at last week. If we take the slant height of a face of the pyramid, which comes to 186.4 meters, and compare it to half the length of a side of the base of the pyramid, which is 115.2 meters, what do we get? Yes, you guessed it, phi. You see, our ancients knew a thing or two about nature that we probably do not. They realized that while there are certain exceptions, there always are, the golden ratio did provide an explanation for several patterns in nature. Therefore, the ancient civilizations revered this number and based their constructions on the golden ratio. Let's now look at a rather famous sequence of numbers in mathematics. The sequence 0, 1, 1, 2, 3, 5, 8, 13, 21 and so on. The sequence starts off with the numbers 0 and 1. Then from that point onwards, each successive number in the sequence becomes the sum of the 2 preceding numbers. Let me explain. So we start with 0 and 1, then we add the 2 together and get the third number in the sequence, which is also 1. Then we add 1 and 1 and get 2. We add 1 and 2 and get 3, 2 and 3 and get 5, and so on. This sequence first made an appearance around 200 BC, when Indian mathematicians started referring to it in connection with Sanskrit poetry. Almost 14 centuries later, a young Italian, Leonardo da Pisa, traveled with his father to Algeria in North Africa, where he learned of the Hindu-Arabic number system and then popularized it in Europe by writing a mathematical bestseller a few decades later. Leonardo da Pisa is today better known by his nickname Fibonacci, and our numerical sequence 0, 1, 1, 2, 3, 5, 8, 13, 21 and so on is known as the Fibonacci sequence. Now, why do you think I'm getting excited about such an apparently random sequence of numbers? Because when you calculate the ratio of 2 adjacent numbers in the Fibonacci sequence, say 8 and 5 or 21 and 13, the larger the numbers get, the closer and closer the results get to 1.618, our golden ratio. Don't believe me? Try it for yourself. And the golden ratio and the Fibonacci sequence can be observed all over nature. For example, the number of petals in flowers such as lilies and buttercups tend to be numbers in the Fibonacci sequence. Don't believe me? Take a look at these images. Why? Because each petal needs to be equally spaced out in order to allow for the best possible exposure to sunlight. In sunflower heads, the seeds start at the center and then move out in a spiral to fill the head. The number of spirals in each sunflower head tends to be a Fibonacci number. In the 1700s, Charles Bonnet claimed that the spiral phyllotaxis of plants going clockwise and counterclockwise were frequently 2 consecutive Fibonacci numbers. An example of this can be seen in pine cones. The seed pods on a pine cone spiral upwards in opposing directions. Each opposing set of spirals matches a number in the Fibonacci sequence, with the 2 numbers most often being consecutive Fibonacci numbers, which gives the golden ratio when divided. In the 19th century, Adolf Zeising discovered the golden ratio in the arrangement of branches along the stems of plants and of veins in leaves. For example, a main tree trunk will grow until it produces a branch, which creates 2 growth points. Then one of the new stems branches into 2, while the other one lies dormant. This pattern of branching is repeated for each of the new stems, creating the Fibonacci sequence. Even human bodies exhibit conformance to the golden ratio. The DNA molecule measures 34 angstroms long by 21 angstroms wide for each full cycle of its double helix spiral. These numbers, 34 and 21, are consecutive numbers in the Fibonacci series, and therefore their ratio, which is 1.619046, is an approximation of the golden ratio phi. In a field study conducted simultaneously in India and Germany some years ago, body measurements were taken of 207 German students and 252 young men from Calcutta. The results confirmed that the total height of the body and the height from the ground to the navel were in the golden ratio. The researchers obtained the value of 1.618 in the German sample for both males and females, and a slightly different average value of 1.615 in the Indian sample. Likewise, the height from the ground to the navel and the height from the ground to the knees is in the proportion of the golden ratio, as is the distance from the wrist to the elbow and the length of the hand. Animal bodies exhibit similar tendencies, including dolphins, starfish, sea urchins, ants, and honeybees. In the case of honeybees, even the ratio of female bees to male bees in a colony tend to be close to phi. In addition, the family tree of honeybees follows the Fibonacci sequence. Males have 1 parent, a female, whereas females have 2, a female and a male. Thus, when it comes to the family tree, males have 2, 3, 5, and 8 grandparents, great-grandparents, great-great-grandparents, and great-great-great-grandparents, respectively. Following the same pattern, females have 2, 3, 5, 8, 13, and so on. A golden rectangle can also be constructed in which the ratio of the sides is equal to phi. The length of this rectangle can then be subdivided in the golden ratio to give 2 rectangles. The length of the smaller rectangle can again be subdivided in the golden ratio to give another 2 rectangles. This process can be repeated over and over again to give us what is known as the logarithmic spiral. Snail shells, nautilus shells, they all follow the logarithmic spiral, as does the cochlea of the inner ear. It can also be seen in the horns of certain goats and the shape of certain spiders' webs. Spiral galaxies, including the Milky Way, also follow the logarithmic spiral, as do hawks' flight patterns when approaching its prey, hurricanes, and human and non-human faces. Interestingly, cross-cultural research has shown that no matter what a person's ethnicity, the closer the proportions of various aspects of a person's face to the number phi, the more attractive the face appears to be. Ever wondered why you can't take your eyes off Angelina Jolie or Brad Pitt, or for that matter, the Mona Lisa? Well, now you know. Ask yourself this question then: are you a living embodiment of the divine proportion? Thank you for tuning in. Join me next week on the Education Hour when we will continue our investigations into number theory, looking at the work of a self-taught young Indian mathematician whose equations help explain the behavior of black holes. This is Shaleeka Jayalath. Stay safe.